In Unit 3, Homework 7, we're going to be looking at applications involving exponential and logarithmic functions. So we have a lot of everything that we've done so far with exponential and logarithmic functions, so some of this will be familiar, and we're looking to apply them to particular problems. So let's go ahead and go through some of the homework problems and see what we can do to help clarify them for you. So for this example, we have a formula, 24.2 times e to this exponent models the population of a U.S. state. So the population is A. Now, t years after 2000. So if we have the year 2020, t would equal 20. So it's the number of years after 2000. We have two parts to this question here. It says, what was the population of the state in 2000? Okay, so A is the population. So the variable that I need to plug in for here then is t. Now, what was the population of the state in the year 2000? 2000 is 0 years after 2000, so I'd have t equals 0. So I'd plug in a 0 up here. So solving, I'd have a equal 24.2 times e to the 0, because 0 times anything is 0. Well, we know e to the 0 is 1, so my initial population here in the year 2000 is 24.2 million. So the important thing to do here is when you are looking at the values, make sure you understand which value represents which variable. So in this case, t stood for the number of years since the year 2000, and then a stands for the actual population. Now part B to this question, so this was part A. Let's go ahead and look at part B as well. Part B to this question, it says, when will the population of the state reach 31.4 million? So this is A. We know A now is 31.4 million, and what we're asked to find then is how many years after the year 2000 will that occur. So we need to solve for t. So this looks pretty familiar to the problems that we were just working on in the previous section. The first thing I want to do is isolate the exponent, the base in the exponent, by dividing through by 24.2. And I want to flip this around so I have my variables on the left. So 0.765t equals 31.4 over 24.2. And then what we can do to get that variable out of the exponent is to take the natural log of both sides. So I have the natural log of e to the 0.07652 equals the natural log of 31.4 over 24.2. Now the whole idea of taking the natural log of both sides is so I can pull the exponent out front. So after I pull that exponent out front, this is pretty straightforward to solve because of course the natural log of e is 1. And then to solve for t, I would divide both sides through by 0.0765. Again, that's 0.0765. Whatever you do to one side, you do to the other. So when I plug this into my calculator, I need to be pretty careful. I need natural log, make sure you have parentheses, divided by, so you have to make sure we're keeping track of that layered fraction. So let's go ahead and plug this into the calculator. We'll have the natural log of 31.4. See if it's going to load here. So second quit, we'll have natural log of 31.4 divided by 24.2. So that's all in the argument of the log. And all of this is divided by the 0.0765. Okay, so let's see what we get for an answer here. Now there's other ways to solve this too, and I'll give you a couple of other options. So as my decimal approximation, I get 3.4046. Now direction will be something like round to the nearest year. So round it to the nearest year. So if we round this to the nearest year, it looks like my options would be 3 or 4. Now we have to keep in mind that this might not be standard rounding. So So when we look at this problem, if it asks us to round to the next year, we'd round this to t equal 3 years. But that's not the answer we'll put in the box. This would be 3 years after 2000. Because if we scroll back up to the original problem, it says the number of years after 2000. So our correct answer that we would put in is 2003. So 2003 would be our correct answer. 2003 is when we expect the population in this particular United States state to be 31.4 million. So be careful that you're not putting in the answer that they're not looking for. This is an intermediate solution, and you need to go to the next step to find your final solution. Now another way we could have solved this same problem is by graphing. So let's go ahead and look at this graphically as well. So our original problem was up here, 31.4 equals 24.2. 31.4 equals 24.2 e to the 0.0765 t. But I can't graph this. I would have to graph this set equal to 0. So I'd subtract the 31.4. Now notice the minus 31.4 is not in the exponent, it's in the base. So let's go ahead and graph this. So I have 24.2, and then I have my exponent, so second divide is my e. That's to a power, that power is 0.0765. And then my variable is t, but I'm just going to plug in an x, just because that's the variable I'm used to working with. And it was subtracting 31.4. So let's go ahead and graph this. It should cross somewhere around 3, so right in here it should cross. Yep, and it did. Let's go to zoom. I usually don't use zoom, I usually use window, but we'll see if we can get this to zoom down so it doesn't go so far out on the x-axis. So I'm going to choose number 6, zoom standard. Gives us a negative 10 to 10 on both the x and the y-axis, and it should cross right around in here. Okay, so now I want to figure out where that's crossing, so then I would go second calc. I choose option 2 to find the 0 or the solution to the function. And I need to be somewhere to the left, and I'm to the left all the way along here. I'm just going to zoom in a little bit closer, and then somewhere to the right. And there's my guess. So 3.40464, that looks just like we got when we did our work by hand. And again, that's giving us the number of years. So if I rounded that to the nearest year, as was suggested, this would round to t equal 3, because we were actually solving for t even though I have the variable x. So t equals 3 years after the year 2000. This implies the year 2003 is when this population will be at 31.4 million. So graphing is a nice little easy way to do this too, and to verify your solutions. So I think with my problems that I would do, I think I would start with graphing to kind of get an idea of how many solutions I'm looking for and what types of solutions I'm looking for, and then from there actually do the handwork and then try and come up with those solutions to match. Let's go ahead and look at another problem from your homework set. And again, all of these are application problems, and I won't run through one of every type, but I'm trying to give you some strategies, multiple strategies to solve these application problems, and then you can apply those to all sorts of different situations. Now this looks like an interest rate problem from a previous section, but this one's a little bit different. Previously we would be given a P, R, compounding periods, or N, don't forget, and a T, and then asked to find the accumulated amount in the account. But if you can see here, we're asked to solve for time t in years. So let's run through here. The number of compounding periods is 2. Amount invested is my principal, that will be P. The amount accumulated will be the final amount in the account. So now I can just start plugging in. So I have 25,000 equals P. P is my principal, 11,500. My interest rate, though, I have to make sure I put in as a decimal. I can't put it in as 6.75. I have to put it in as 0.0675. Number of compounding periods is 2. That means twice per year, semi-annual. And then in my exponent, I have 2 times t. Now what I'm trying to do is solve for t here. T is in my exponent, so if I want to run through this with logs I can, or I can just graph this to start with to see what I have. So if I were to graph this, this would look like 11,500, 1 plus 0.0675 over 2 to the 2t. I think I'll use an x there, and then I'd subtract the 25,000. So this is equal to 0. So this is what I would do for graphing. I need to set it equal to 0. So let's go ahead and graph that. Okay, so that's y equal. So we have 11,500 parentheses 1 plus 0.0675 divided by the 2 compounding periods, close parentheses. And then in my exponent I need my 2x. Now if you have a caret key that shows up instead of exponents, make sure you have parentheses around the 2x. And then I have to subtract the 25,000. Now I'm looking for t, and it says round to one place is needed. So let's see what we get here for a solution. It's working. We can see it's spinning up here, so that tells me it's working. It might be outside of my window that's showing, because I'm trying to take 1,500 to 1,600, so I'm trying to earn $100 in interest. And it's going to take a long time, it looks like. So let's go ahead and change my window. It's not going to take a negative amount of time, so let's just worry about the values for my positive x direction. Let's see if it crosses out here. You can see it's spinning, so it's still thinking. Okay, there's my answer right here. So this was 25, so about half would be 12, so this is probably maybe around 11. To find out for sure where this is, you'd go second table, and you're looking for where the values on the y-axis change from positive to negative or negative to positive. So for the trend that we're seeing now, we can see that it's switched right here between 11 and 12 years. So this is not giving me my solution, it's giving me the location of my solution. It's saying, you know what, if you look between 11 and 12 years, that's going to be your value for t. So let's go ahead and pop that in to our graph as well. Okay, so let's go ahead and look at our graph again. And again, we figured out it's between 11 and 12 years. So let's go second calc, choose option 2 for the 0 or the solution of the function. Now right here where it says left bound, you can click over if you want. It's going to be hard though because this is almost a vertical line. So I'm just going to put in 11 because we just saw in our table that our answer was between 11 and 12. There's my right bound. So you can see I'm on either side, and then go ahead and hit enter for our guess. And it says this is my 0, 11.69. So that's my answer, 11.697188 years. So graphing makes these really easy, and of course we're going to solve them by hand as well. But now I know what I'm shooting for my solution. So this would be t equals, now up in the directions it said round to 1 decimal place. So if I rounded this to 1 decimal place, I'd have 11.7 years because the 9 would round the 6 up. So this would be my solution that goes here, 11.7 years. Now, how would we do the same work by hand? Well, we'll start with our original, and we'll isolate the exponent and the base, and then we'll kind of work from there. So I think we'll need a new page for this. So by hand, we would have 25,000 equals 11,500, 1 plus 0.0675 over 2 compounding periods to the 2t. So to get started, we want to isolate. So 11,500. 11,500. I'm going to switch my sides here to put my variable on the left. And on my right I have 25,000 over 11,500. So you could either take the log or the natural log of both sides. Doesn't matter. Well, the whole idea of taking the natural log of both sides is so I can pop that 2t out front. So I have 2t natural log 1 plus 0.0675 over 2 equals the ln of 25,000 over 11,500. Now the whole idea is to solve for t. So what's in the way of t being by itself is the 2, and then this big natural log argument. And of course, whatever you do to one side, you do to the other. Everything over here cancels except for the t. I get t equals this. Now, I don't like to do any intermediate reductions because a lot of times what happens then is my final solution is off due to rounding error. So I'm leaving everything out in full form here. Now, when we plug this into our calculators, we have to be really careful because we have so many layered fractions here. Now, a couple of other things that are going on with this particular problem. I could simplify like the 0.0675 over 2. I could divide both sides through by 100 here, or top and bottom by 100, but I'm just going to plug it in as is. So let's go ahead and plug this in. Let's do ln of 25,000 over 11,500. And I'm going to start with this big set of parentheses here. So the ln of 25,000 divided by 11,500. So I'm closing the parentheses on the log argument, and I'm closing the parentheses on the numerator. I'm opening the parentheses on the denominator, so I have 2 times. And this is where I have my new log argument, the ln of 1.0675, etc. So I have the ln of 1 plus 0.0675 divided by 2. So I'm going to close parentheses on the log, close parentheses on the denominator, and hit enter. And you can see that I get the same value that I just got, I think, from my graph. 11.697118 is what I had before. Oops, I'm going to copy this, and I have the same thing here, 11.697188 here as well. So whether you do it by hand or you do it graphically, you can see that our solutions verify. Now, one thing that you want to keep in mind here is exact form versus decimal approximation. So if my math lab were to ask you for the exact form, this is what they'd be asking you for right here. So this is exact form. This is your rounded answer. Now let's go ahead and scroll up and see what the original problem said about rounding. I can't remember. It says rounding to 1 decimal place, so that would be 11.7 years, which is what we got when we did our graphing as well. So you can do this by hand or by graphing. I would always try and do the graphing first because there's a lot less room for error, but you should double check both handwork and graph work. Now, all the problems that you're going to be looking at in this section are all a little bit different, but the same idea applies to all of them for solving. You have a graphical approach, you have solving by hand approach, but the thing you need to remember is when you're setting them up is to make sure that you're identifying which variables represent which numbers, because that'll be one of the tough parts here. Okay, so for this particular problem, we have a graph, so this piece is called the graph, obviously. And then we have a model, and so for our model, that's this in parentheses. So f of x equals 8 plus 43 ln of x. So when it says refer to the model, make sure you're referring to the model, and when they say refer to the graph, refer to the graph. Now, percentage of new cell phones with cameras X years after 2002. We kind of covered that up. So X represents the number of years after 2002. Okay, so part A, it says use the function to determine the percentage of new cell phones with cameras in 2007. Does this underestimate or overestimate? Okay, so 2007, that's X years after 2002 would be 5. It's 5 years after 2002. So I would have f of 5 equals 8 plus 43 times the natural log of 5. So let's go ahead and plug this into calculators and see what we get back out. 8 plus 43 ln of 5. Whoops, this is off the screen. 8 plus 43 ln of 5. So 77.205. Now this is a percentage. So this is an estimate of the percentage. So round your answer to the nearest percent is needed. So this would round to 77%. So that's the answer that would go here, is 77. Now that is based on the model. Now the second part to this question says, does this underestimate or overestimate the model? So let's go ahead and pull that question in, and then we'll see how we can compare. Okay, so let's look at the model. In the year 2007, what happens here is the graph, which is the actual amount, for 2007 says 68%. So the actual amount is 68%. Now, so what we're trying to decide is this underestimate or overestimates? Okay, so let's read this carefully. Does this number, so does 77% overestimate or underestimate? Well, 77% is higher than 68%, so it would seem like it would overestimate. Okay, so you have to be careful. What is it comparing? Which value is it comparing against? And then it says, how much does it underestimate or overestimate? So that's our next question, so let's pop that one in so it's familiar. Might run out of room here. So let's squeeze it in here. By how much? Well, the difference between 68 and 77 looks like 9%. So you would just subtract the difference between the two, and so that's how much the model is overestimating. Okay, now there's a part 2 to this question as well. I guess part 4, because we're already on part C, I think. It says, if trends show from 2003 to 2007, use the function to determine by which year 86% of new cell phones will have a camera. So let me pop that question in so you can see what we're looking at there. So this is the same problem that we're just working on. We're just adding another part to the question. So if we remember, our model was f of x equals 8 plus 43 times the ln of x. Okay, so if we go back and look, let's see what x stands for. X stands for the number of years after 2002. So let's just note that x equal number of years after 2002. Okay, it says use the function. So we're not going to look at the graph. We're just going to use the function to determine by which year 86% of the new cell phones will be equipped with cameras. So I think we should just plug an 86 in here. I don't think we need to use its decimal form. And then what we want to do is solve for x. So to get started, we'd subtract 8 from both sides. 86 minus 8 would be 78 equals 43 ln of x. Divide both sides through by 43. And I have ln of x, I'm just going to switch sides here, equals 78 over 43. Now remember, we don't want to know what ln of x is, we want to know what x is. So remember, ln of x is log base e of x equals 78 over 43. So if this is my base, this would be my exponent, and I could rewrite this as e to the 78 over 43 equals x. Okay, so let's figure out what e to the 78 over 43 is. Calculator. So here's my e, exponent 78 divided by 43. So it looks like 6.1 or so. Now remember, that's not going to be my answer. We need to, look and see what the question is. Does the question say the number of years or in what year? So it says in the question, by which year? Round your answer to the nearest year. So this would be, rounded would be 6 years after 2002. So I think that we'll be looking at 2008 here. Okay? Now you have to be careful. You don't want to do any intermediate rounding, because when you do intermediate rounding, you can kind of throw your answers off a little bit. So 2008 is when that's going to happen. Now, another way that we could have solved this is by graphing. So let's go ahead and look at this by graphing. So if we look at this graphically, I have this 86 equals 8 plus 43 ln of x. I could go ahead and subtract the 86 to get it set equal to 0. So I could have 8 plus 43 ln of x, and then outside the argument of the ln I have minus 86 equals 0. Now if you want to simplify that a little bit, you can, like combine the 8 and the negative 86, you can, but it's not necessary. So let's go ahead and look at the graph. So we have 8 plus 43 ln of x. Make sure you close a parenthesis on that. So 8 plus 43 ln of x, and then we had to subtract over that 86. And let's go ahead and graph this. Might have to change our scale, and here we're crossing. Let's go ahead and do second calc. Let's choose option 2 to find the 0 of my function. Now I need to be to the left, and right now that star is to the right. So let's hit enter once we get it to the left, enter once we get it to the right, and find our solution. So you can see here that we have 6.13 for my solution, which I think is exactly what we have up above. Let's compare that. Yep, 6.13465. So this is my solution for the number of years. So this would be t equals 6 years, but I have to add that to the year 2002, so I get 2008 for my answer. Okay, so I get 2008. I like the graphical approach because I like the visual of it, but I can also see where learning how to do the handwork and being able to check it with the graph would be really beneficial as well. There's a formula that's going to come in handy for this section, and it's based on exponential growth and decay. Now parts of this formula are going to be really important to know what they represent, and we have to know which part represents exponential growth and which part of change represents exponential decay. So the model is A equals A naught e to the kt. Now this 0 is not a base, it's A naught. It means our initial value. So let's go ahead and define everything here. So this value of A equals the amount remaining. And this is if we're talking about exponential decay. If we're talking about exponential growth, it's the amount that everything has grown to. A naught is our initial amount. So what we started with, how much we started with. Now K is going to end up representing some sort of a factor of growth. So it's a rate of growth. And T, of course, is equal to the time in years. Now the variable that represents growth or decay is K. So this is either growth rate or decay rate. Now, how do we decide which is which? If K is greater than 0 or positive, we're growing. If K is less than 0, it's decaying. So again, it's really important that we look at those particular values. Now, one other thing that we could look at is what is happening at t equals 0. Well, t equals 0 means before we even start, no time has passed. So at t equals 0, what ends up happening then is our amount is A naught. At t equal any other time, our amount is represented by A. So this initial amount is either given or you're asked to solve for it, but it's always the amount that doesn't change. And then once we plug in and calculate things, then we get our final amount that we're looking at. So working with these problems, it's going to be important that you be able to solve for the different variables. So knowing whether that value of K is positive or negative will help you determine growth or decay. So let's run through one quick problem where we're looking at exponential growth and decay. Okay, so we're given our exponential growth or decay function, a equal a naught e to the kt, and then we have a little bit of information. It says 7 years ago the population was at 1,600. Today only 1,000 of the birds are alive. So this definitely looks like a decay situation. Once the population drops below 300, the situation will be irreversible. When will this happen? Okay, so we have a couple of different ways that we could work this problem depending on how you look at it. It doesn't end up really mattering what was going on 7 years ago. What matters is what's going on today. So today our population is 1,000. Okay, now from here I have a value for K and I have a value for T, and I want to know when this is going to happen at 300. So this is how I'd set up my initial problem, and if you see, this is where the situation is kind of not good because I have two variables. So I need to come back over here and use this information from 7 years ago, the 1,600 and the 1,000, to find out that value of K. So I need to find K to plug into that equation. So 7 years ago my population was 1,600. And now it's 1,000. So this is my initial value. This is my ending value, e to the k, and this happened in 7 years. So what we can do now is solve for k. So we divide both sides through by 1,600. And you have to be careful here because you don't want to do any rounding. So I have e to the 7k, putting my variable on the left, equals 1,000 over 1,600. Well, if I divide both sides through by 100, top and bottom, I'd have 10 over 16. 10 over 16 reduced to 5 over 8. Now to solve for k, I'd take the natural log of both sides. So I'm going to have the natural log of e to the 7k equals the natural log of 5/8. So the whole reason of the natural logs is to pull that 7k out front. So I have 7k natural log of e equals the natural log of 5/8. Natural log of e is 1. So I have 7k equals the natural log of 5/8. I don't want to reduce any of this, and then divide it by 7. So this is what k equals. Natural log of 5/8 over 7. I don't want to find a decimal approximation for this. I want to take this and plug it in right there. So I have 300 equals 1,000 e to the k. Now k is equal to the natural log of 5/8 over 7 times t. So now I'm trying to solve for this t. So I'm going to divide both sides through by 1,000. And I have e to the natural log of 5/8 over 7t equals, let's see, 300 over 1,000. That would reduce to 3 over 10. Then we go ahead and take the natural log of both sides, and I would graph this actually, but that's just how I would look at it. Is, you know, if you sooner you can graph this, the better, because you might make some mistakes in between. So the whole idea of that is so we can pop this exponent out front. So I'm going to have natural log of 5/8 over 7 times t equals natural log of 3/10. Now remember, when I pop this out front, the natural log of e goes to 1. So to solve, I divide both sides through by the natural log of 5/8 over 7, natural log of 5/8 all over 7, and that's what my solution is. T is equal to this value. Well, we need to find out when this is going to happen. So this is an exact solution. We need to apply this to find a decimal approximation. Now it says the population will drop below 300 birds approximately blank years from now. Okay, blank years from now. So I don't have to say the number of years after 2002 or anything like that. So let's do second quit. I have the natural log. Scoot over here and have a look of 3 divided by 10. Close parenthesis. Now I'm going to divide this by, and I'm going to put up a set of parentheses, a natural log of 5 divided by 8, and then that is divided by 7, and I close parenthesis again. So here I have 17.93, and let's see how that compares to how they would like us to round. Again, you can graph this right away too, once you find that decay rate and plug it in and graph it. So it says, do not round to the final answer, then round up to the nearest whole number as needed. So when we look at this solution, if we round up, it looks like it would round to 18 years. So this would round to 18 years, and that would be my solution. So it says to round up. So if this was 17.2, I'd still round this up to 18 because it tells me to round up. So when you're working through this section, if you have any questions on the application problems or the notes, please bring them to class. Stop by my office hours, or the Mac Center is always open as well. Good luck.